So first of all, first thing first, I am not an expert in algorithmic game theory. So I have read, I have tried to this. So there will be some issues which I may not understand fully. So I would appreciate if you comment if I am not saying something right. That's one thing, or if I do not able to prove everything correct, because there is one thing which I have spent like 3-4 hours, but I still don't know whether like what it is. Okay, so I'll tell you what it is. Okay, so the I'm trying to cover this chapter on best case and strong Nash equilibrium. So this is a chapter 15. Okay, best case and strong Nash equilibrium. Best case and strong Nash equilibrium. I think this is what is called SNE. Okay. 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 So this is also, you can think of this what I call a network cost sharing game. These are also called okay. So the model of this games are, so what is a model? So you are given a graph GVE. So that's, so you're first of all, so this is like a network, okay, and you have k agents, okay. So this graph can be both either directed or undirected, okay. So this graph can be either directed or undirected. So network cost sharing games will have this, and then you have some k agents, okay. What you have, and for also each is carries a fixed cost, okay, fixed cost. So there is some positive quantity cost that you are given to this, okay, and there are k agents, okay, and okay. Agent I has origin vertex OI and destination vertex DI, right. So you have an agent I, it has some origin vertex and some destination vertex, okay. And what is her strategy? So let us say strategy space of SI is all paths from OI to DI, right. So agent I has a origin vertex OI, destination vertex DI, okay. And what is her strategy? Her strategy is all paths from OI to DI, meaning he or she can choose any path from OI to DI as a part of his output or whatever it is called in this, okay. And what is an outcome of this game? Outcome of this game is, so before I go and give you some motivating example, so output of this game is basically every agent will choose a strategy from its strategy space, right. So basically it is going to return something from this. So basically if this is what strategies are and this is what strategy space is, then what it is returning? It is returning some path P1, P2, Pk. So that's what it is returning, okay. Okay. And what is the semantics? So, the semantics is that a sub network is formed by these paths, right. So, think of this way, that you forget all other edges which are not appearing on this path, right. So, basically you are like, basically you can think of this as V. So, you have vertex set, you forget all the edges that do not appear on this path, that is it basically, right. You forget all the edges that do not appear on these paths. Okay, all this fine. Okay, so we will talking about. See, the problem is that since I do not have the full picture of this field, because I have never taught this course or I am not working. So, first I will try to define what formally it means, and then try to give a motivating example that can capture it. Okay. So, it will be slightly different than what probably Susmita would teach. Okay. So, you are given a graph, right, you are given an agent, and agent chooses a path, and a sub network is formed in this. So, but what are they objectively trying to achieve, okay, right? What are they objectively trying to achieve? Okay. So, the kind of places where it is used is to people view this gamma e, or I use gamma e, right, cost gamma e as a fixed establishment cost. What I mean by a fixed establishment cost? Okay. Suppose I think this is a very good example, that a community is formed here. A community is formed, right? Set of houses. Okay, this is a new community that has come, right, and your main road is this, right, and now you are trying to get connectivity from this road to this community which has formed maybe somewhere slightly older place. Okay. So, now the fixed, so think of this gamma e as a fixed cost to construct this road connecting this main road to this place, right. So, it is a fixed cost, right, whether one person uses it or 2% uses it or all of these people use it, this is a fixed cost of constructing a road from a fixed cost of constructing this side road, right. So, this is the way it should be viewed. You understand my point? Like, so now if it is a fixed cost, then what you think is a right measure for these people to share? If it cost, I mean, then like it's whether you live in a small house or a big house, you are going to use this road as likely as this person or that person is. So, a general model will be that we all will share the cost of this, right. So, if it is a fixed cost, it is not because 10 people are using it or 100 people are going to use it, it is like more or less it is not going to vary. So, you fix the road, you got the road made, now whether you use or I use or 100 people use, it does not matter. So, this is in this kind of scenario, this kind of games or networks are used, right. So, which also means that this gamma e, right, should be shared equally among the agents that get to use this, right. So, if I do not use, like some people had this, some people constructed that, I mean, why will someone who uses some other road is going to pay for this road until? So, it makes sense that only people who are using these establishment, what do you call, contribute towards establishment cost. Okay. Okay. Okay, fine. So, this is how this should be viewed. Or for example, this is one example, or maybe like this is something which you see quite naturally occurring in this, is that whenever some new community or something comes, generally there is some hub of internet here somewhere, and now you set up some fiber network or something here, like some fiber network, and that is going to serve lots of people. So again, this is an example of a fixed establishment cost, and then so now it's a fixed establishment cost which is shared by a lot of people. Again, whether you're living in a small house or a big house, if you're going to use internet, you're going to use internet. Like, so these are really naturally occurring examples that I can think of. Okay? Okay, so this tells us a nice way of looking at these things. Okay, and what is this nice way of looking at this? So agent cost is defined edge by edge. Okay, so agent cost is defined edge by edge. Okay, I think you would have seen similar to, I think, what is called routing games. Have you seen these routing games? Some selfish routing games. So there also you define everything edge by edge, like every, right? And now the point is, so just to make this example bit more cohesive, is that if multiple agents use the same edge E, then what should they do? They should split the cost. Okay, then they jointly bear the cost comma I. Okay, and so there are also models. So for us, okay, they split equally. Okay, but I can very well envision that in many situations you may not split equally. For example, look at some community, like, so for example, I live in a community here, right, and we have some common spaces, right. So if I live in a big house, there is a big area around me which I am responsible for, which is outside, but it's largely who I am going to use it. If you have a small house, you have a small courtyard or this which you are. Now other people can also use it, but large fraction of that cost should come from me, right. Small fraction of cost could come from other people. So we could very well imagine scenarios or situation where you may not, like, there could be some formula or could be some percentage by which these agents share this cost, right. But at least for today's lecture, we will assume that we are in a situation where whatever it is, everybody shares the split equally. Okay. Now what happens is that, okay, so now I don't know, like these things. So you must have seen, like, in the language of cost minimization games, okay, what is the cost of an agent? What is the cost of a agent? Okay, so suppose you are given in this outcome P, right, you are given this outcome P, P1 to Pk, outcome is given. So I am interested in what is the cost of Pi, what is the cost of, not Pi, cost of a agent I is the right word. Okay, I think this is not how it is. So this is why I am saying, right, Ci of P, right, what is the cost of agent I with respect to the output P, right. So this is basically, so what, he is only going to use his path, correct, he is only going to use his path, right. So what path did he choose? A path Pi he chose, right. So I am going to say E in Pi gamma E divided by how much? How much is he responsible for? Depends on how many times that path, that edge has been used by any of these people, right? So, he is only paying that share of the cost, like, because we are equally splitting. So, if there are 10 agents which are sharing this edge, then it should be gamma E by 10. That is his cost to that. Okay. So, this is gamma E by Fe, where what is Fe? Fe is though G E appears on Pj. Okay. So, what is a frequency E? Is a cardinality of this set, right? Number of paths this edge appears on, correct? So, this is the cost of an agent. And what is the cost of path system? I think the cost of path system, these could be people who could have defined also is this. I could, like, what is the cost of the whole system is this, but they define it actually slightly different, which is same, but like I think they do not use C of this, they use cost of P. Okay. So, I think this is same, but let us see, but how they define is summation. I think they define all those edges that appears on this path. So, basically E in E. Okay. So, E in E, frequency of E is at least 1, okay, gamma E. I think they are same definition, no?
Yes.
Right, because look at gamma E, right. So, here also look at that edge that is equally split in each of this. So, if it is split into 5 people, then, but like basically the point is, look at any edge occurring in this, the total according to the cost of this is sum the cost of each of the edges. But if I define this way, then this is also fine, because that edge, if it occurs 5 times, then it is 1 by 5, 1 by 5 counted 5 times. If it is used 3 times, 1/3, 1/3, 1/3, use 3 times. Okay, good. So, this is what the cost of this is. So, our objective is to come up with a strategy. Okay. Yeah, they also say this is same. Okay, so this is not something. Okay. So, what is our objective? Our objective is to come up with strategies. Okay. Objective is probably to come up with what is this called? This I know is called a strategy. What is this P called? It has a name, no? Right, strategy profile, correct. Objective is to come up with strategy profile C that minimizes the cost. Is it fine? Okay. Okay. Now, the book gives us an example. I do not understand very well why, but there is a book gives us a new example of, can I rub these things? Okay. So that I can keep it. Okay. fine. Okay. Okay. So, the example this book gives us is what he calls VHS or beta mix. Beta mix or beta mix, I do not know what this is called. Beta mix, max, beta max. Okay. So, we just want to build some intuition about this network sharing games. Okay. I think beta max or beta mix something. So, what happens to this? So, this is like these were two technologies which was I think appeared in early 1980s in US. Okay. Did Trump become president again? Okay. So, right, and and people believe that this is much better technology than VHS. Okay. Now, the network we have is this. Okay. Fine. Okay. Cost is k, cost is 1 plus 1, this is origin and this is destination, OI, DI, whatever you want to call. So, OI, DI are the same. Okay. So, basically you are deciding to choose, agent chooses whether to use this technology or this technology. Basically choosing this edge means I decide to choose this path, which means I am going to use this, and if I choose VHS, I am going to use this. Okay. So, according to you, if this is what it is, what is the best strategy profile? Okay. So, my question is, what do you think, can you come up with a strategy profile? Okay. Come up with strategy profile that minimizes strategy profile P that minimizes cost of P. What do you think? Can you come up with a strategy profile that minimizes cost of P? Epsilon is some small quantity which is greater than 0. Okay, let us say 1/100. Okay, it is just something. Okay.
Everyone chooses the shortest path.
Okay. Okay, very good. Hopefully, I will be able to explain something interesting. Okay, okay, very good. So, okay, so the best optimum best is that everybody chooses what? Let us call it everybody chooses B max, because then the cost of this is how much? 1 plus epsilon, right? Okay. So, this is amazing, right, that everybody would have chosen beta max, right. Okay, wait, okay. So, it seems this is also called, this is also PNE, pure Nash equilibrium. Do you remember the definition of pure Nash equilibrium? Huh? Right. So, what was PNE's definition was, okay, let me tell, we were saying something. Why?
The number of agents choosing the second one is 1, then it is 1. K is 1.
Okay, no, K is some quantity which is exactly equal to the number of agents in the network. So, K is like this K that I chose here, this K is the number of agents in my game. So, if there are 100 agents playing this game, K is 100. Okay? But now, what was the definition of PNE? Okay? So, the PNE definition was, let us see why. So, what was pure Nash equilibrium definition was? So, a strategy profile S, right? A strategy profile F of a cost minimization game. So, this is like a kind of a cost minimization game. Okay, of a cost minimization game, our strategy is pure Nash equilibrium if for every agent I in 1 to k, if for every agent I in 1 to k, and every unilateral strategy SI, right? Every unilateral, what do you call, every unilateral deviation, they call it deviation SI prime, like basically everybody is playing this, like if he chooses to replace, so basically what is the strategy? So, this is strategy, then like let us say this S is like some S1, S2, Sk, this is my strategy. I decide not to play, so I am, so okay, so I decide not to play Si and I try to play Si prime, right? This is all that it means, that I decide unilaterally to forget using this, and this should be true about everything Si prime in S. Then look at his cost with this deviation, right? His like is like amount, his cost in the strategy is less than equal to how his own cost increases if he deviates. So, this is like, this is what they write, Ci Si prime S minus I. So, basically this means you delete Si and replace with Si prime. Is it fine? Is it correct, Sanjay? Right? This is called pure Nash equilibrium. So, is it PNE? Let us prove this, that this is PNE. So, whatever this we decided is a PNE. Okay. Why it is pure Nash equilibrium? Because suppose an agent decides to forego him and replace it with VHS, because that is all the choice he has. Now, what is his cost then, right? So, if I change my profile, some agent I changes from beta max to VHS, what is his new cost? So, new cost will be how much? New cost of what they call VHS in P minus I, okay, in that line is greater than Ci of P, right, and this is greater by how much? This is K, and how much he was paying here? Huh? It was paying this, right. So, it could be, so the point is that, right. So, this is why this is a pure Nash equilibrium, right, because anybody, if he or she deviates from this strategy, his personal cost is much higher. So, it is better for him to follow the protocol. Okay. But unfortunately, there is more, there is one more PNE in this game. What is that? All taking the VHS, right? Okay. So, look at, let us call this, okay, this is like P hat, everybody taking VHS. Why is this a pure Nash equilibrium? Why is this a pure Nash equilibrium? You understand my point? Why is this a pure Nash equilibrium? It is a pure Nash equilibrium because, so what happens? So, suppose some ith agent, I guy changes from what? From, let us say, VHS to P beta max, whatever that means. But now, if we compute, look at the cost of Ci of, let us say, beta max, comma, let us say P hat I, no, P hat minus I. What is this quantity? What, how much he is going to pay? 1 plus epsilon, right? This is going to be 1 plus epsilon, which is greater than equal to, if the same guy would have, which is exactly equal to 1, because everybody shares equally. So, this is also pure. So, what I am trying to tell you is that, I mean, cost wise, this was a better technology, right. Maybe this is, and their cost is also more, but if this technology is not available in my, say, near my house, or what do you call, in the shop near my house, am I going to use that technology, or I am going to use this VHS technology? You understand the point? Like, even though this is cheaper, better technology, now what happens is that if that is not available where I stay, all I am saying that there are other factors why people might choose this Nash equilibrium over that, right. Although it is from the perspective of an agent, this is cheaper, this is cheaper. But if it is not even available because there was new technology, and this, in few years everybody followed this, and the beta max technology was wiped out, like they were out of the market. Okay. At least this is what the book says. Fine. Is it okay? Okay. Another concept that people have used, again I am trying to understand, okay, is what they call POA, okay, which is, what is they call? Price of anarchy. And what, how is the price of anarchy defined? So, if I understand correctly, the price of anarchy is defined as follows. So, okay. Okay, is system performance, okay, system performance with strategic players, system performance with strategic players divided by system's best response. At least this is what it says, whatever it means. System, best possible system performance. Unfortunately, this is all that I found in the book. I don't know what it means. You understand? Are there other definition? So tell me, maybe it will be useful for me.
Numerator is the worst possible system performance, equilibrium system performance.
Okay, so please tell me, maybe. What is it? Tell?
System performance and worst possible system performance and equilibrium.
Worst, thank you. Worst possible system performance in equilibrium, okay, divided by, this is fine, right? Right? So, what is the POA for this system? Here. So, worst possible system performance in equilibrium, which is K by 1 over epsilon, right. So, it is roughly K, right, because epsilon is tiny, so it is roughly K. All good? So, this is all that I wanted to say. Excellent. So, we all understand. Oh. Okay. So, in fact, matching upper bound, exercise 15.1. Okay. So, here is a lemma, okay, which I am not going to prove, it is an exercise. So, this is the exercise you should try to do. In every network games, right, every not network cost sharing game, it is called, because this is what we are doing, every network cost sharing games, okay, the price of anarchy of pure Nash equilibrium is at most K, the number of agents. That is all that I want to say, right. So, if you look at this network sharing games, I mean this example of K or 1 over epsilon is that you cannot make it worse than this, right. So, every pure Nash equilibrium, like price of anarchy of any pure Nash equilibrium is at most the number of agents. So, it is like it is not more than K, right. But the natural question could be, so every one is not worse than the number of agents, but does there exist some pure Nash equilibrium which is not as bad as K, but slightly better than K, or maybe like close to optimum, you understand. So, the question which derives this theory is, does there exist PNA, okay. So, what is this that derives? does there exist pure Nash equilibrium that is close to optimal? Okay? Do you understand the point? So, this tells us, this example tells us that it could be as bad Hk, and this lemma tells us it is never worse than K, but this guy tells us, but okay, it's fine, I get it that you can be as, but look at this example, I mean, can I find a pure Nash, like, but in this example there is a pure Nash equilibrium which is exactly equal to the optimum, right? So, in that sense this is 1. But it could be there is a possibility that my best cost, because at the cost I am not asking you to come up with P1 to Pk which has to be equilibrium, right? All I am saying to you, you come up with the paths that minimizes this thing. But now I am saying to you, is there, so in this example it just happens that my cost like P1 to Pk, the which optimize this cost, happens to be pure Nash equilibrium in this example. In this example, cost P is 1 plus epsilon and we know it's P and E, right? So, in that sense, at least for this example, POA is 1. Not P, like, like for this question, it is 1. There exists a P and E which is optimal, but there could be situation or scenarios where this guy, the cost and the pure Nash equilibrium could be very far apart, right? And this guy tells us that this only tells about principles POA, right, and bioptimal. It could be as bad as K. So, the question is there some, can we find a pure Nash equilibrium which is much closer to the optimum, which may not be pure Nash equilibrium? Does it even exist? Forget about even computing it. Does there exist a pure Nash equilibrium which is not too far away from the optimum, which, like, the point is there may not even exist a P and E which is equal to the optimum. We will see in a minute. Okay? So, do you understand the kind of question that we want to address in next half an hour, 40 minutes? Okay? Okay, so at least I hope I have built up rightfully. Okay. See, I had to build my story, no? Okay, but okay, so now we will look at another example. Okay. I think I am also learning things. Okay. Okay. So, now we understand the definition of P and E. So, can I rub this? Okay. I will keep this definition of POA because I also need to process this. Like, I have not used this definition ever in my life. So, it is like Sanjay, is it going okay?
Yes, it is.
Okay. So, this is a question which is going to drive our discussion. Does there exist a pure Nash equilibrium that is close to optimum? Okay. Okay, so now I am going to give you another example which is called opting out. Okay. Okay, so this is called opting out. Okay, this is not going good. It will take some minutes to dry up. Okay, so let us not waste time. Let me use the whiteboard for some time. Okay. So, I am going to define another game, another example, and that will lead us to the kind of conclusion that we might be able to derive. Okay. Okay. So, this game is called opting out or opting out network. Okay. So, it has only one destination. Okay. Okay. And but there are multiple. So, let us say this is we were calling O1, right, origin 1, origin 2, origin k. Okay. Okay. And what is the cost on each edges? Okay. So, cost on each edges is OI is 1 over I. So, this is going to be 1 over k, this is going to be half, this is going to be 1. Okay. Okay. And there is another route via V. So, it is like either you go like this or you can go and come like this. Okay. And it is like you roam around. So, the cost of these guys are 0. So, you can go here and this is 1 plus epsilon. Okay. So, now, so this is my network. So, please tell me two things. Okay. What is the best cost strategy? What could, in this example, what is the best cost strategy? I am not talking about equilibrium or something, nothing. I am talking about the best cost strategy. What is the best cost strategy here in this example?
One plus epsilon.
Right. So, if everybody chooses to just meander around to V and zoom via that, then that is the best. So, look at this strategy P. So, what everybody chooses, let us say path O1 V and then di, O1 V di, OI V di, OK V di. So, what is the cost of this? This is cost of P is 1 plus epsilon, right, because it is just basically the sum of the weights of the edges in this network. Okay. So, now my question to you is P PNA? Is P a pure Nash equilibrium? Huh? Right. So, what happens if agent K does the following? What does agent K does? It says, I will not, for me, I will do P minus K and replace with my OK di. Okay. Right. So, what is the cost what is a C? So, let us call this P P prime. What is the cost of K in P prime and what is the cost of K in P? So, this is 1 plus epsilon by K, everybody equally shares, but here how much it is? 1 over K, right. If epsilon is strictly positive, then this quantity is less than this quantity, right. So, this is strictly less than this, right. So, this is, and hence this is not a pure Nash equilibrium, right. At least this strategy is not pure Nash equilibrium. So, we have just seen an example that the best cost strategy may not be a pure Nash equilibrium. Okay. Okay, but notice what happens, right. But the moment he shifts here, right, the moment K shifts to OK D, what happens to OI? OK minus 1 now, right. Now, OK minus will say, hey, now K minus us are sharing this cost. So, now 1 plus epsilon K minus 1 people are sharing its cost. The guy says, okay, but then why should I leave here? Let me go to OK minus 1 to D because I only pay 1 by K minus 1. So, gradually everybody will shift. So, now look at the following strategy. So, look at the following strategy P tilde, right. Look at the following strategy P tilde, which is basically everybody chooses to go right. But then is it a Nash equilibrium? Is it a equilibrium? Is it a this is P tilde a pure Nash equilibrium? It is, right, because if he moves to the other path, he pays 1 plus epsilon, right. So, this is because other strategy costs him 1 plus epsilon, which is larger than its cost in P tilde. Okay. So, the next question is how expensive is this? Like, what is the cost of P tilde? What is the cost of P tilde? So, we got a pure Nash equilibrium, right. So, what is the cost of P tilde? It is summation 1 over I going from 1 to K, right, which is equal to ln n. Is that fine? So, notice here that at least it gives us some intuition. So, we came up with this opting out example, right, where the optimum cost is like 1 plus epsilon, but it is not a pure Nash equilibrium, and we did find a pure Nash equilibrium, but then its cost is ln n. So, in this situation, what will be POA in your example? What is price of NRK here? What do you call? Worst possible system performance in equilibrium, like it is less than equal to, because we do not know, maybe there is some other strategy, I do not think there is like ln n by 1 plus epsilon. Okay? Because maybe there is some other strategy which is better, but like definitely POA is less than equal to ln n by 1 plus epsilon, and if you stare it, at least in this example, this is exactly equal actually. Okay? Okay, so that brings us to the next concept, okay, what is called price of stability. Okay? You can take a picture because I will move to the board. Any question, guys? you will anyway be able to see this. It's not, this way I wrote it very big enough, but at least it will not go that far that you can't see this example. But anyway, we don't need this example. Okay, all good? Okay. So now I'm going to define the concept what is called price of stability. My God. Price of stability. Okay. This is called, this is a theorem. Okay. Okay, this is called price of stability theorem. In every network cost sharing game, every network cost sharing game with k agents, okay, with k agents, you know, okay, okay, fine. In every network cost sharing game with k agents, okay, with k agents, there exists a with k agents there exists a pure Nash equilibrium with at most Hk, where Hk is the kth harmonic number, Hk times that of an optimum solution, Hk times that of an optimal solution. You understand what I am saying? Right. So, basically what this theorem is telling you that in any network cost sharing game with k agents, there exists a pure Nash equilibrium whose cost is not more than ln n. So, whatever example you saw here, this ln n example that you saw is basically you can achieve this for any cost sharing network games. Okay. Now, notice what POS says, worst possible system performance in equilibrium. What is this PSA tells us? Price of stability, or POS is basically an optimistic version of price of anarchy, because here what we are saying, the best possible system performance in equilibria divided by optimum system performance. Is it fine? Right? So, this is the difference between, it is called POS, right, a price of stability, or this is what is called price of stability. Okay. Okay. So, this is an what they call optimistic version of price of anarchy, right, because here optimum system performance is there. What is the worst you can do in equilibrium? This is what is the best you can do in equilibrium, right. Okay. So, this is like, in my opinion, this is like a worst case running time, and this is like sometimes sorting can also be done in linear time. Why? Because already the array was sorted. Sorry, bad joke. Okay. Okay. And this is where I do not understand some things. Okay. So, what they, I think you must have seen a proof about some atomic self-first routing. Have you seen the proof for atomic self-first routing? Okay. So, what we are going to, what is the proof strategy is going to be very similar to what you seen for atomic self-first routing. Even if you do not remember, do not see, like it is okay, it is fine. But like it seems earlier proofs as this. So, basically what they are going to do is they are going to define some measure, okay. They are going to define some measure or what they call potential, okay. 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 So, how it is going to do? So, the route is we are going to define a potential function, okay, and I am saying that minimizer of my function is of my potential function is a pure Nash equilibrium. Okay. So, I will define a potential function. Okay. So, this is a step 1, and then you prove that the minimizer of potential function is a pure Nash equilibrium, and so this is let us say some phi of p, and then third step is relate phi of p and cost of p, and then you get the equivalence. It is like a normal approximation algorithm, right. So, the point is that if I relate phi p and cost p, and phi p is related to p and e, then I also get related to p and e and cost p, no, right. So, this is just like a normal approximation algorithm, right. Like what do we, so you want to do ILP, right, this is what you want to approximation, you do with LP, right, and if you have relation between LP and ILP with some gap, and that gap is your approximation factor. So, something very similar. So, at least this is how I view it, is like I do not know how to do cost p. So, I relax it to phi p and relate phi p to my p and e or whatever it is, and then go back. It is like, so the what is that called not gap, what is that called, yeah. So, the LP and ILP, what is that called, gap, no, you solve LP and then the ILP, what is it called, the rounding, right, rounding gap, right. So, you round, basically what you take LP and you round it to ILP. So, the rounding factor is your approximation factor, because LP I can solve it, right. So, when I went to LP to ILP, I have some rounding factor, right. So, this is exactly what it is. So, I want to relate cost p, I do not know how to do it. So, I relax it to get to a potential function, but when I go here I lose some factor, when I go from here to I lose some factor, right, and that lose factor, if we can show that it is HK, we are happy, because then I will be able to relate all these things. Okay. So, I mean I am just giving you, and probably this is the reason why people can write LP, primal, dual even in this context and start to round or do things. You understand what I am saying? Because this reminds me of that. I do not know, I am not from the field to know, I have not seen too many proofs in this area to actually, but I am 100% sure that whenever you have some optimization function, right, these potentials are used as a relaxation, like Lagrangian relaxation of something, and this, what is this? I want to understand some function, I do not know, I relax it, which is easier to understand, like in continuous optimization you do some multivariate relaxation or Lagrangian relaxation, you understand the study and you see what is the gap between that study and what we want, and that is your approximation algorithm. For example, you write vertex cover, no, and you do relax, what is the gap between those two? Rounding gap, half, factor 2, and that is a factor 2 approximation, right. So, in that context I am saying to you, So, if you keep that in the mind, so this is a usual idea which can be applied invariantly in most places. So, this potential and this, they might look magical in the beginning, but it is a natural way of how to relax that I have a much more control over computation of those things. Okay, guys. So, the potential they define, and if they say that it is adapting the potential function from the proof for this atomic selfish routing, they come up with this potential function. So, what is the potential function they come up with? Phi of p, it is summation E on E, summation I equal to 1 to k, right. No, this is not what they do. F e. Okay? Do you see what they do? So, this is the potential function they define. You go over each edge, you add gamma e by I, how many times? F e times. Notice in the cost p, you only add gamma e by F e, right, for each agent, right, I equal to 1 to e. So, what is this is same as you write, what can I write here? This I can write, let us see, gamma e I can take out, and what is this? F e 1 over I, is it okay? Right, this is what it is. Now, something which I do not understand and I try to prove, so if we both can together prove, is that what it says that minimizer of phi p, right, is a pure Nash equilibrium. I do not understand why, at least this I do not understand, I do not know why is this true. Okay. So, let me try to give a proof without assuming that, and I will try to see if I can prove it myself or anybody can prove it. It says it's just that I am not you, but suppose I give you that this is a minimizer, then how can we go about proving it? So, what it says that a function which minimizes this potential function is okay. Okay. Some important remark. Okay. Okay. What did we find best possible performance in equilibrium, right? So, all we will be able to show that minimizer of phi p is PNE. Okay. That does not mean that this is the best possible PNE, best performing PNE. You understand? It may not be true. It's just a PNE with which, so if I can say that, hey, look at this PNE, even for this itself it is ln n, at most ln n, then if I replace with even better performing thing, then my approximation can only go down, it cannot increase. That is it. Okay. So, now let us try to prove, okay, let us try to understand what happens. Look at gamma E, gamma E. Gamma E is less than equal to gamma E times summation I equal to 1 to F E 1 over F E, sorry 1 over I, because this is a positive quantity. So, this is less than, which is less than equal to I going from 1 to k 1 over I, because I have only k agent, I have only k agent. So, frequency can be upper bounded by k, F E is upper bounded by k, because I have k agent, you are using k paths, right. So, an edge can only be used by all the k agents. So, its frequency is upper bounded by k. So, which implies this is correct, right. Okay, of course, and we are only talking about for every E such that F E is greater than or equal to 1. Okay. So, now let us, if you sum this left side, you sum over this over E in E, F E is greater than or equal to 1, gamma E, this is what your cost of P is, right, correct. Then I can write this is less than or equal to H k times cost of P, because I sum over this, H k will come out, this is summation gamma E. So, this is this. Okay. So, what did we derive from here? So, from here we derived cost of P is less than or equal to, when you did all this summation gamma, all this thing, which was nothing but right. So, cost of P, I can write it is less than or equal to basically. So, think of this way, I can write it like this, right, E in E, F E greater than or equal to 1, gamma E, and that term I equal to 1 to, correct. I can say this, and this is what, but what is this quantity? That is exactly phi of P is. This is the quantity which is phi of P is by definition here, right. So, this is phi of P. Okay. 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 Let P denote, let P denote the PNE minimizing my potential. Okay. And let P star and let P star be an optimum outcome. Like P star is an optimum outcome, right. That may not be PNE nothing, this is optimum system performance. Now, what can I say using all this inequality is that what is cost of P? Cost of P is less than or equal to phi of P. Here, look at this. Cost of P for any this is less than or equal to phi of P. Basically, we just added more term. That's all that we did. Like to each edge we added some positive, like greater than 1 multiplier. So why it will be less? The right way of looking at this is C. For every edge, I have added some quantity which is strictly greater than equal to 1, and that's a much more cleaner way of looking at it. So this is right. But what is phi of p? Phi of p is less than equal to phi of p star. Why? Because I was looking at some potential and I try to minimize it, right? So p star is also a possible object that could have minimized it, but he did not minimize it. No? So p minimizes it. You understand my point? So the point is, look at all the strategies. So every strategy is in the feasible set of minimizer. So in particular, if p star is also, and if so phi of p star, the reason why you did not choose p star is because maybe phi of p is less than equal to phi of p star, or maybe p equal to p star, for all that you care. I don't know. But what is phi of p star? What is phi of p star? Anything is right, is hk times, right, cost of p star. Are we done? Cost of p by cost of p star, right, is at most hk, right. So what we showed now is that, hey, cost of p, so the best way of doing is this, look at what is that called, price of stability is equal to best performance pure Nash equilibrium, okay, divided by optimum system performance, right. This is less than equal to, okay, less than equal to performance of p, some p pure Nash equilibrium divided by opt system performance, right, which is equal to what is this is equal to, because this is what I meant, is cost of p divided by cost of p star, which is by your choice is less than equal to hk. Done. Okay. But the one thing which we did not prove, why is minimizer of phi is pure Nash equilibrium, right? I mean, because our whole proof relied on the fact that the minimizer of my potential function is a pure Nash equilibrium, and this I don't know how to prove. At least today I don't know how to prove it. I tried. Maybe it's easy. It's just that I'm not used to thinking in this along these lines. Could be a reason why I did not manage to prove it. Okay.